Mountain ranges fascinate human beings. They have for as long as people and mountains have been present on the planet. Early in the relationship, people sought to explain the mountains' existence. Their peaks hidden in the clouds, they were often thought to be home to deities or were deities themselves. Creation legends developed. Cherokee Indian stories credit the Appalachian Mountains to the flight of a buzzard, its wings sculpting the valleys and leaving the mountains in high relief. The Himalayan mountains also have many creation legends. In one, the rugged landscape is the result of a massive struggle between deities that left the terrain scarred and broken. Today, scientific methods used by geologists explain mountain building quite differently. However, the evidence hidden in their slopes remains one of massive forces acting within the Earth. In this video, we'll examine these two mountain chains, the Appalachians and the Himalayas, from a geologist's perspective. Although half the globe separates them, and their outward surfaces could not appear more dissimilar, the forces that form them are the same and come from deep below. The age and structure of the Earth has intrigued humans for centuries. Early hypotheses to explain rock formations and composition could only be based on physical observation. Geology was not recognized as an independent scientific discipline until the middle of the 18th century. As the discipline developed, new methods to determine the composition of rocks and the way they were formed became known. The 20th century saw significant technological advances. The structure of the Earth was hypothesized by measuring reflected seismic waves from the interior. Scientists identified the outer and thinnest portion as the crust. Below the crust is the mantle. It is a solid, but intense pressure and heat makes it very plastic. Over time, it moves similar to putty. At the center is the core. It has a liquid outer portion and a ball of near-solid iron at the center. Using the processes of radioactive decay, geoscientists now believe the Earth is 4.5 billion years old. Over that expanse of time, the appearance of the surface has constantly evolved. For the first half-billion years, volcanic activity dominated the surface. Gradually, it began to cool. Initially, geologists believed the cooling of the Earth's crust caused it to crumple and fold, creating the landforms. But in 1912, Alfred Wegener proposed the continental drift theory. It was based on the shapes of continents, common fossil records on different continents, and climatological data. Wegener's theory stated that continents had once been connected, but had separated. He could not explain what force moved them, and his concept was not accepted by everyone. Almost 50 years later, in 1960, Wegener's theory was supported when Harry Hess measured seafloor expansion and thus movement. This phenomenon, along with seismic evidence, supported the concept of pieces of the crust and upper mantle moving as large plates. The plate tectonic theory is that convection currents within the mantle move the floating plates slowly over time. 7 such tectonic plates hold the continents and the Pacific Ocean. There are many smaller plates around the globe. Plate boundaries are broadly determined by actively forming oceanic crust at oceanic ridges and the places where oceanic crust is being destroyed or consumed through subduction. The mountain-building ability of plate movement is the force that created the Appalachian Mountains and is still pushing up the Himalayas today. The formation of mountain ranges by intense horizontal, then upward displacement of the Earth's crust is known as orogeny. Such mountains exhibit plastic folding, thrust faulting, and other compressional deformations. With the help of 2 University of Tennessee geologists, Drs. Bob Hatcher and Micah Jessup, we will see proof of the force at work. The Appalachian Mountains stretch from Canada to Alabama. Viewed from space, they resemble a wrinkled brow that runs in a northeast-southwest direction. The southern range in Tennessee and North Carolina averages about 3,000 feet in height. The highest point is 6,684 feet at Mount Mitchell, North Carolina. Today, the power of the mountain-building process has been masked. Millions of years of erosion, along with current vegetation, soften the visual contours of the slopes. Nevertheless, geologists say the Appalachian Mountains are the result of a massive continental collision more than 300 million years ago. Today's globe gives no clue of how this might have happened. However, if you travel back in time, quite a different story is revealed. Evidence suggests that 500 million years ago, the continents were largely contained in the supercontinent Gondwana and two smaller continents. Moving forward in time, it is hypothesized that the supercontinent of Pangaea began to form about 360 million years ago. As Pangaea forms, the plates that contain today's North America and Africa collide, and the mountain building begins. As the two continental crusts are pushed against each other, layers of rocks begin to override other layers. The pressure also folds the rock layers. Faults are formed, and gigantic rock masses slide parallel to those fractures. Some masses move for hundreds of miles. More and more material is uplifted. Today, the continental crust beneath the mountain range is some of the deepest on Earth, measuring more than 30 miles in places. A second powerful force was shaping the Appalachians at the same time they were rising. Erosion, the power of wind, water, and time, sculpted the outward surfaces we see today. Pangaea begins to break apart around 200 million years ago, and the image of today's globe starts to take shape. Bob Hatcher is a distinguished scientist and professor at the University of Tennessee. He was the first to apply concepts of plate tectonics to the southern Appalachians and has authored 9 books on the subject. His tectonic maps of the Appalachians have been used in subsequent international research. His work reflects many years of traversing great stretches of the Appalachian Mountains on foot. We will visit several sites Hatcher has chosen for evidence of continental collision in the Appalachians. Our first site is along the border of South Carolina and Georgia on the Chattooga River.
We are located at Woodall Shoals on the Georgia-South Carolina border on the Chattooga River, which is a wild and scenic river. We are here because the rocks exposed in this very large exposure formed at depths of 10 to 12 miles in the crust some 360 million years ago. They then were uplifted, eroded many times until the fairly recent geologic history of this area, and the last time only a few million years ago, during which the present-day landscape formed.
The exposure of rock here was created in part by dynamite. A logger named Woodall attempted to open up the stream in order to better float his logs downstream. The folded layers vary in size. Some are the size of automobiles, others only a few inches.
One of the things we like to look at here is the evidence that these rocks were buried so deeply in the crust. And this is in the form of not only the folded layering that you can see here very easily, but also these pieces of white material that you see within the layering. This material has been melted out of the old rocks, and you don't get that kind of thing happening except in the deep crust. It consists of very coarse-grained igneous material, that is molten rock material, that crystallized in the other rocks that we've been looking at. It crystallized very slowly, so the crystals of muscovite or white mica, quartz, and feldspar became very, very large. The first impression you might get is that this entire mass of rocks and the layering, the way it's wrapped around and everything, would be caused by the work of water. The work of water is the last thing that happened here to produce the river channel.
From Woodall Shoals, we fly to Chunky Gal Mountain. This road cut exposes a suture between microplates formed 460 million years ago. A suture is a type of fault that joins two crustal blocks that originated miles apart. These rocks and the suture are much older than the Appalachian Mountains, but contained within them. They have been exposed by erosion and highway construction. From Chunky Gal Mountain, we move further west to the area of the Sequatchie Valley. The valley is about 200 miles long, and in places the sides are nearly vertical. This valley was once a ridge formed by arching of an anticline. An anticline is a convex upfold caused by compression. Over the years, the exposed rock of the anticline has eroded away to form the valley. On the western rim of the Sequatchie Valley, a road cut reveals more information.
We're looking at a group of sandstone here that was deposited in an ancient delta system that developed when the Appalachians were rising up following the collision of Africa and North America. This is debris from the rising mountain chain, and the rocks were deposited and ultimately consolidated into sandstone and shale and also into coal. The sand that formed the sandstone probably came in and was deposited over the organic matter from plants that had accumulated in the swamp that then destroyed the plant life there. Then the plants were compressed over time into a layer of coal. The whole thing about what we're seeing here in the contrast between sandstone and shale is a contrast between strong and weak units, and the coal is even much weaker. And so we're seeing deformation that occurs by compression in strong and weak units. We were seeing deformation that occurs by extension, pulling things apart in both strong and weak units up above.
As we move along the exposed rock face, Hatcher points out more and more evidence of crust movement frozen in the forms.
The layering is horizontal here, or nearly so, but then the grooves on this particular surface are near vertical. And these are grooves on the fault surface, and they tell you which way the fault moved. This is something we use all the time in the study of faults, both active faults and dead faults. The fold on the right has only one small fault in it, perhaps because the thin shale beds that we have in here took up the deformation, whereas with the fold on the left, it's more sandstone dominated, and the layers broke, producing several more small faults with displacements of a few inches over to the left side here.
The Dunlap Road Cut is rich with details of the mountain building process, but some of the stories written in rocks are best viewed from altitude. Here near Caryville, Tennessee, among the ridges of the Appalachians running northeast to southwest, suddenly a ridge makes a 90-degree turn and heads in a northwesterly direction next to a valley underlain by the Jacksboro Fault. This is known as the Pine Mountain Thrust Sheet. The sheet extends some 100 miles into Virginia, where it again ends against a similar northwest trending valley. The collisional force coming from the southeast direction moved the rock sheet miles before stopping here. From Pine Mountain, we move southeast to Wallen, Tennessee, and another road cut.
It's very hard to believe, but where my hand is located right now is on rocks that have actually moved 300 miles from where they started out and where they were deposited. This great slab of rocks is the product of the collision of Africa with North America about 300 million years ago. This sheet was 3 to 4 miles thick, and erosion has reduced it to where it is today. The shale, for example, here is the kind of rock that a fault like this, a thrust fault, can move with great ease, especially if it's wet, just like the rocks today here are quite wet and water is actually flowing out of them. And so that helps with the lubrication of the sheet and the lubrication of the fault zone to permit it to move great distances.
Here we see compression forces that bent incredibly tight folds in shale.
These are shales that were deposited in very deep water in a basin that formed on the North American continent during the first events that helped form the Appalachians.
Geologists believe Pangaea started to break up about 200 million years ago. About 50 million years ago, a new collision of tectonic plates began. The Indian plate is actively crashing into the Asian plate. The mountains resulting are the Himalayas. The Himalayas follow a 1,500-mile arc along the northern border of India. The chain has 100 peaks higher than 23,600 feet, with Mount Everest being the tallest at 29,029 feet. These elevations are thought to be similar or even lower than the elevations of the Appalachians when they were formed 300 million years ago. Of course, the Himalayas are still growing. Even as these mountains build, they too immediately start eroding. The effects of water, both freezing and thawing, as well as rain, are relentless. The movement of glaciers carves away their surfaces, and rivers run flush with material washed from the mountains. This collision zone is where Dr. Micah Jessup and his students spend research time. His research has brought him here 9 times. The work is in collaboration with professors in China and India. It is funded by the National Science Foundation and the National Geographic Society. Jessup has co-authored nearly 60 publications regarding his findings along the chain.
Welcome to Tibet. This is the 3rd week of a month-long research expedition. We're interested in how India and Eurasia collided. The collision began about 50 million years ago and was accommodated by rocks. This is a great example. These are sedimentary rocks that were deposited as horizontal strata. Sedimentary rocks accumulate as layers, and then during the collision between these two plates, the layers were folded, and this is a fantastic example of this. You can see these small folds here and larger folds, all accommodating crustal shortening that began at about 50 million years ago and continues today. One of the interesting things for those of you in the Appalachians is this is very similar to folding that you see there that occurred hundreds of millions of years ago.
The material they seek was once buried up to 8 miles in the crust.
Sometimes you think you know what we're going to find when we go into an area, and then when we get there we find something completely different. So that's one of the really nice things about this kind of exploration-driven science.
Their findings map out a geologic past and present for the collision zone. The rocks in effect act as recording devices for the collision that is taking place.
We can look at the minerals in a rock. Does it contain things like garnet? And then we can do chemical analyses of the garnet and figure out the pressures and temperatures that that rock reached. And since pressures and temperatures increase as you get deeper into the crust, we can figure out where the rocks were metamorphosed. Another example is we can look at grains, crystals in the rocks that contain radioactive elements that accumulate over time, and we can date those and figure out how long those minerals have been there and when those rocks formed.
Jessup's team collects rock samples from the surface all along the Himalayan chain. They also travel to the Tibetan Plateau in search of samples.
The Tibetan Plateau is one of the biggest uplifted regions in the world. And when it was uplifted, tens of millions of years ago, it changed global climate circulation patterns. And so these mountains aren't just rocks, they are dynamic systems that interact with climate, seismicity, and lots of other things that have implications for us as a society.
On a playing field that is 4.5 billion years old, the study of plate tectonics is a very young discipline. What causes the movements can only be hypothesized. Fuller understanding of the movements and how they occur will provide important insight into earthquake occurrence and frequency. Still, the ability to track events hundreds of millions of years old adds to the knowledge of what we now know is a very mobile and moving Earth.